Hello everyone, welcome back to the ARC seminar. Today we have Linhao to tell us about dynamical tides.
Yeah, so hello, I'm Linhao. In case you don't know me, I'm a first year grad student in physics, and I'm organized in further just like the same as Nicholas. So I'm going to talk about dynamical tides in stars today. So I guess I will use a lot of these words, so maybe just keep an eye on these two. Yeah. Okay, so we're going to talk about tides. Okay, and before talking about dynamical tides, we actually first need to talk about what are equilibrium tides. So equilibrium tides are basically the tides that you already know about. That is what is happening on Earth. So on stars, they are basically, or more like physical way of saying it is they're just a hydrostatic deformation of a star. So imagine you have a star. So this is your star, and you have a companion here, which is not necessarily this small, but just that. Yeah, this is a companion. And you have gravity here, and certainly you have a tidal force, because the gravity you're feeling here is different from the gravity we're using Newtonian gravity throughout the lecture. Yeah. So clearly the gravity you're feeling here is different from here, so that will create a deformation of the star. And if the companion is actually orbiting this deformation, there will be a phase lag in this deformation and the sort of the tidal forces. And the deformation will look like this. Yeah. And you see that basically this part of the fluid is like following the orbit of the companion. And there's a phase lag. And the reason is that the tides here, they're also dissipating energy, so there's some friction in that fluid, so they're also dissipating energy, and so there must be a phase lag in here. And if we call that phase lag angle to be epsilon, so it's actually, there's a defined thing called tidal quality factor, which is defined here. 1/Q, so Q is the tidal quality factor, is defined by so this is like an integral of the total energy dissipated during a circle. So you're doing this orbit, and this is like the total energy in the tides. So basically, this factor characterizes the the amount of energy dissipation we're going to have. And somebody shows that it's actually for equilibrium tides, there's a physical interpretation that is basically tending to epsilon. So one thing you need to know from here is that the larger Q, basically the smaller the energy is dissipated, and the smaller this angle will be. So if there's no dissipation here, then Q is just infinity. So the larger Q, the larger energy dissipated. Okay? So this is our story about equilibrium tides, which is actually proposed a long time ago. So this factor is defined by Peter Goldberg there in 1966. So our main character today will be dynamical tides. So what is a dynamical tide? This. Okay. So dynamical tides are basically tidally excited oscillations. So I'm so sorry that Nicholas is not here for this moment, but
He's getting a mark.
thank you. Thank you for coming back. So we're going to talk about what you talked about before. So Nicholas once gave us a lesson about what is about Escrow Seismology, which is basically the internal oscillations of a star. So you have a star here. For example, this is a convection core. You have some oscillations around here. So clearly, when you have a companion, let's say here, then the tidal force will just excite the oscillations, and they will reach some amplitude. Of course, they are also damping. So basically, dynamical tides are just these excited oscillations. So they are no longer the deformation of the star. So you cannot actually see that the star becomes that shape. So these are dynamical tides. And if you really want to know about what are actually those oscillations are, just ask Nicholas. Yeah. And yeah. So one thing I want to point out is that this Q factor that we're going to talk about, mention at the end of the talk, it is initially defined just for equivalent tides. But for some reasons, the observers are just too lazy, so they are continuing using this Q factor to characterize the energy dissipation, even for dynamical tides. And in that case, the Q factor has no such a physical interpretation, which is such a pity. But I mean, I don't know why they're measuring in all their papers. They're just measuring this Q factor. We have to translate it back to some real physical quantities. But anyway, okay. So I gave you an idea about what are the TEOs. Sorry. Tidally.
You might want to use the other marker. The other one.
Should I just?
Sure. Yeah. Okay.
So I told you dynamical tides are tidally excited oscillations. In short, TEOs. Okay? So then let's try to solve it. So the basic idea is just we have a companion, has some tidal potential and tidal force, and excites the oscillations. So how do we actually calculate this tidal response? So we're starting from very first principle, since I think maybe all of you are physics students here, including me. So, so we have some basic fluid equations. And if you don't remember any of them, just ask Nicholas again. Yeah. So basically, they are like the same equation that Nicholas has introduced when solving for stellar oscillations. So this is the perturbed, we're working in linear series, by the way. So this is the perturbed continuity equation. And we also have an energy equation, which is, so rho is the density, and this is the displacement here. We have the energy equation, which can be related to this. So this is energy. And we also have the momentum equation. Delta P over rho plus del P over, what is this? It's the cosine difference. Yeah. Sorry, I need to check what is this. It's not printing correctly. Delta rho minus the perturbation of the gravity field, but we have one more term which is the tidal force provided by the companion. this is not included when we're just solving for the oscillations in one star. And that term is the del of the tidal potential, which we denote as U. So this is the momentum equation. And clearly we also have a Poisson equation for the gravity potential. That is basically phi equals 4 pi g over rho. And notice that all these small delta, they are all these small delta, they are they are the Lagrange perturbation variables, and this big delta here, they are the Lagrangian perturbation variables. So they are related by this. So this is the variable Q. So the Lagrange and so Lagrangian variables are related by this. Okay. So you notice that we have 1, 2, 3, 4 equations, 4 variables, which is P, rho, phi, and C. Right. So when we're solving for the stellar oscillations, basically we don't have this term, and we just combine all of them together, and we're solving for dispersion relations, right? So usually in that case, we're combining them in a way that we finally have one equation with one of the scalar variables. But since we're interested in the what is the eigenfunction of the displacements, how the oscillations actually perform. So we can combine all these equations to a more complicated form, which is never done in practice, but this is a formal theory. And we combine all these equations to a simple equation with only one variable, C. And that equation is you have a second derivative of C plus some linear operator acting on C equals minus W, which is a tidal force. Okay? So in case you're interested what this operator is, I don't want to write it down, but just take a look. It's this one. This thing here. So basically, you only need to believe that we can combine all of them together, and this is indeed a linear operator. And then, yeah, it's super complicated because nobody actually do that when they're solving for real mode. They're using scalar variables, but it's in principle possible. Yeah. Okay. So let's try to solve this equation. So we notice that we can actually, if we don't have this external, tidal potential, then basically this equation just becomes this thing equals 0, and that is just the normal stellar oscillations that we can solve. And I'm pretty sure you all know how to solve it because Nicholas already told you. So the solutions are: we assume that all the variables have a Fourier dependence on the time, and the eigenvalue omega alpha. So basically, this is just telling you that C is a linear operator C equals cos alpha. So this is a free equation. Is omega alpha squared. Alpha, right? And you see that this is then how do we use this to solve this equation? I mean that is too simple, right? We just we define an inner product, which is defined by C alpha C beta equals dv rho C alpha objective. So with that definition of the inner product, we can further show that the C operator is Hermitian. So that means this C alpha, they form a complete basis. So basically that means you can assume that the general solution to this equation is just a combination of all this C alpha with this coefficient A alpha, just time dependent. And then you substitute it into here and take the inner product, and basically this is Hermitian, so that means all these eigenvectors are also normal. Then you can get your equation for the coefficients, and that is A alpha 2 dot plus omega alpha square A alpha equals the inner product of C alpha. Okay? So basically you solve the tidally excited oscillation for this case. You just find the free solution, which is just normal state oscillations. You decompose it, and then you use this equation to solve the coefficient. Right? But note that this is the non-rotating case. That is, the star is not rotating. From the momentum equation, we don't have a Coriolis first term, we don't have a zero-figure first term. So, but we actually cannot talk about tides when the star is not rotating, because tides are just they're depositing angular momentum onto the star, so the star must be rotating. So basically, for a rotating case, we need to add one term. Actually, it's two terms, but I'll explain to you later. Add a term to this equation, and the equation becomes another linear operator dot plus okay. So this B term is a Coriolis first, so that is defined by B C equal to omega spin cross product C dot. So this is a term that is clearly linear. And this C, so there's another centrifugal force term, which basically add one term into the C operator. So the C operator here is different from that. But you can also show that that does not change, that does not change anything, because the added term is also Hermitian, and it's, so basically we just use the same thing here, and it's not going to change a lot. But what really changed a lot is that if you're actually thinking about solving this equation, you might think, oh, I can do the same as before. I just solve the free equations. So the free equations, then the eigenfunction, they satisfy sort of this. So say that, okay, I just solve this, then I expound everything in terms of this C alpha, then I solve the coefficient. But there is a problem. What is the problem? The first thing is that this C operator is Hermitian, but is this operator Hermitian? Is this operator Hermitian? Actually, it is. So is it? So the first problem doesn't exist. But the second problem here is that if you really look at this operator, or if you really compare this to this, you'll find another problem that, so let's move this eigenvalue into here.
So I just want to ask something like related to this analogy between these two problems. So on the left, we're defining omega squared to be the eigenfunction of like the free eigenfunction. Sorry,
Yeah,
the eigenvalue of like the C operator basically. But here this is
Right.
now the eigenvalue of
no, but it is. So basically, you are still doing this. So these omegas are not the same as that ones, but you can treat them as still as eigenvalues of this new operator. But this introduces a problem, and you may already notice that you see that this omega of alphas, this omega appears in the left hand side. That means that even if you can solve this, they are not a basis, because for different omega alpha, these are different operators, right? Even if it's a Hermitian operators, they are different operators, so they do not form bases. So how do we solve this problem? So if we actually look at how we end up here, if we actually look back, we say the problem here is that we have this additional term that is proportional to the first time derivative of Xc. Right? In the non-rotating case, you only have the second derivatives of Xc. So basically, you can just have a normal eigenvalue problem. But here you cannot. So how do we solve this? So can anybody remind me, like, is there a way that we can sort of, if we only have like first time derivative or second time derivative, then everything's solved. But we have a combination of them both. So can anybody tell me that is there a way that we can try to modify this equation so that it only has second derivative or first derivative? So remember that in classical mechanics, the Newtonian equation of motion is second derivative, but it has an equivalent formula that is basically only involves first order derivative. And what is that equation? Right. Yeah. So that is actually the point here, and this is first introduced by. I'm trying to find the people. Yeah. So Dyson and Schutz. Otto Ryder and Dyson and Schutz. 1979. The point now that to solve this equation, you actually need to change your configuration space to the phase space, and you need to expand your eigenvectors in the phase space. So you can have your you can have an equation that only involves the first order time derivative. So let's try to translate this equation of motion into Hamiltonian form. So the first thing is that you can notice that this equation of motion can be generated by a Lagrangian that looks like this. Sorry, that's not okay. Then you just use your techniques in classical mechanics to calculate the canonical momentum, which is basically the Lagrangian, the derivative of Lagrangian to the C dot, and that gives you this. Then you have your Hamiltonian, which is pi minus L, which is 1/2 pi minus 1/2 bc squared plus 1/2 c plus the tidal term. Here is minus tidal term is a negative. Then you can write down your Hamiltonian equation of motion, and we're going to write it down in the matrix form. Because basically you have variables, the time derivative of the configuration, the time derivative of the canonical momentum equals a matrix that is 1/2 b minus c plus 1/4 b squared minus 1/2 degree. And the configuration and the momentum plus source term, which is the tidal potential. And if you call these giant variables, call it, sorry, what is this? What is this letter called? Zeta? Or is that, yeah, that is zeta, yeah. So if you call this variable zeta and this matrix an operator T, and this is the external term F, and then you find that we have the first order time derivative only. And you see that, okay, we're so happy that now we only have first order time derivative. So we can solve for the eigenvalues here.
All right, so I have a question then.
Yeah.
So yes, so we motivated this by saying we can decompose this equation the Hamiltonian way into first order differential equations. But what is the advantage in this case of not just doing the naive thing of defining pi as c dot, and you could just go over there to that equation and decompose it into two first order equations in an arbitrary way.
I'll translate all this back to that form.
Well, what I'm asking is so here we define this new variable basically because of the way that we do this in the Hamiltonian way, we define this pi to be this particular.
Yeah.
But what is the advantage of this particular formulation? We can also set pi is equal to c dot or something, and then we could also decompose it as
then
first
you will
order.
not have a form like this one, right?
Well,
I mean, you can translate everything back, and I'm not.
You'll get
I'm going to show you that this is not actually as simple as it looks. There are still problems here. You cannot avoid the problem just by transforming it to a more beautiful form, right?
Right.
But the problem here is that, so you might think that we can follow the case of the non-rotating case that we solve for the eigenfunctions and we use these coefficients, right? But here's the problem. This T is not Hermitian. So this is Hermitian clearly. C is Hermitian, 1 is Hermitian, but B it is not Hermitian. So it's only I times B is Hermitian. So that means even if you find the eigenvectors of T, which we may call it delta alpha, so you find all this and you find all the eigenvalues, let's assume. Since this is not Hermitian, so first, they do not necessarily form a basis. Second, they are not orthogonal to each other. So yeah, so basically we're transforming our problem here to a problem that this vector they do not form a basis. So how do we solve this? So I don't know if you remember about Jordan normal form in linear algebra. Yes. Hermitian operators so let's switch back to linear algebra. Yeah. By saying this operator is not Hermitian, it's equivalent of saying that this matrix is not diagnosable, right? So you cannot find all these beautiful eigenfunctions that form bases and also going to each other. But we know that for every matrix, we have this Jordan normal form, which is basically our way of dealing with things. So basically, you can construct a set of this is very mathematical, but so let's assume you already have all these eigenvectors. So you can construct a set of eigenvectors that is called. Sorry, you can construct a set of vectors that is called delta alpha sigma, omega alpha, So they form a basis, and for different alphas, they are orthogonal. But with this small level sigma, so not all these are eigenvectors of T, but I don't know. I don't know how much you remember what Jordan normal forms, but yeah. Okay, basically I'm just telling you that in principle you can construct a number of other vectors other than the eigenvectors of T that form a basis. And that will introduce you a lot of very technical mathematics, but you can do that. So that means you can construct such a basis, and you can use that basis to your expansions. But when you are expound your general solution to this equation, those coefficients in each Jordan block, those coefficients are actually coupled to each other. So I don't think I have time, or I don't think it's necessary to go through the details here, but yeah. Basically, if you know about Jordan normal terms, you think that you know that it is possible. Okay, so to make our life easier, let's assume that all these vectors here, let's assume that all our Jordan chains have length 0. Another way of saying it is that we just happen to have this basis to, so it happens to be that these eigenvectors can form a basis. So that means we are trying to, and I will show you actually that why these usually do not affect the results when I talk about applications of it. Okay? So from now on, we just assume that we have these eigenvectors, and they just happily form bases. So by introducing Jordan normal form, you basically have something more than it, but that will just make everyone's life harder. So let's assume that we're doing a simple case here. Okay, but we have not yet solved another problem. That these bases, we assume they have formed bases, but they're still not orthogonal since this is not a Hermitian, right? So that means we actually need to define a set of vectors. Let me start from. I never, actually, before studying these subjects, I never know that Jordan normal forms have actual applications. Yeah, I was too surprised too. Yeah. Okay. So we now have these eigenvectors that satisfy this equation. Right? And we're doing our expansion. And we assume that they're just a basis, so we can do that. The problem is that these things, they are not necessarily orthogonal. So that means we actually need to find the left vectors to this. And those left vectors satisfy the equation. The Hamiltonian conjugate of this T operator minus I omega alpha the conjugate. So we denote them as chi. So they satisfy this equation. And they also satisfy, since they're left vectors, so they satisfy the orthogonal relation to the right vectors.
Okay, hold on. So I have a question. So you're saying the set zeta alpha, you're saying this is not necessarily orthonormal, right? We assume that the Jordan chains are all length 0, which means it's diagonalizing, right? So in that case, why aren't, I guess this is not a Hermitian operator. What is T is a Hermitian operator, right?
T is not.
Not a, okay. I see.
It's just, if T is, then these are naturally a basis and also
okay.
But T is not. Yeah.
And when we say left vectors, we mean like a dual basis, right?
Right.
Okay.
Yeah. So I will show you in a single case that why there exists such left vectors, and that is actually down here. So for more simplicity, we assume that there's no like degeneracy for the eigenfunction. Sorry, this is zeta. Yeah. That means that for the same eigenvalue omega alpha, there's only one. Okay. Then we can sort of define a matrix, which is so in the literature they call it a symbolic matrix, but I think it's actually a symbolic matrix times I. So we can show that if this delta satisfies this eigenvalue equation, then m delta must satisfy. If delta alpha satisfies this, then m delta alpha must satisfy this, and that is due to there are some quantities about this matrix. For example, m, the Hamiltonian conjugate of m, factor equals m, and equals minus of m. So that could prove that Hamiltonian conjugate of m times t times m equals minus Hamiltonian conjugate of t. And with all this, I'm pretty sure you are all familiar with, so I just tell you that this vector is actually satisfies this. So that means the chi vector must be proportional to this vector. So the proportional coefficient we just denote as b alpha.
So is this property is this a property of like the Hamiltonian decomposition, or is there a way to see
which property?
Like this the fact that like m times zeta alpha satisfies this?
Well, this is I would say it's mostly mathematical. It's just you can construct. I'm telling you like how to construct your left vectors from this from the right vectors.
So this is like I can do this for any t, or like this is just an identity, just plug it in.
I think it's for any t. For any t, yeah, it's so basically you verify this. You know? Maybe there's some like hidden. I'm not expert on all the symplectic structures of these things, but maybe there's some hidden mathematics inside it. But anyway, the point I'm making here is that you can construct the left vectors in terms of this. And to calculate this b alpha, you just use this quantity, and that will give you a result of b alpha. So basically, just substitute into this should be. So basically, you just substitute into it, and you will find that b alpha equals 2 times epsilon alpha conjugate, 1, where epsilon alpha is omega alpha plus 1/2 I C alpha B C alpha. Okay. So if there's actual degeneracy exists, so basically this analysis is still valid. Just this B becomes a matrix, and you are going to take the inverse matrix of, you substitute and you get a matrix, and you just take the inverse of it. Anyway, it does not change. It does not change the point I'm making that this is possible. Okay. So now we have these left vectors. We have this coefficient. So we can try to get back to our tidal equation, which is, so our equation states this. I will just call it here. Right. So we're getting back, and we are able to so trying to find basically you're gonna have an equation that gives you the evolution of A, which is A alpha dot plus I omega alpha A alpha equals the left vectors cross inner product of F. And remember, F is 0 and the tidal potential. And you already sort of expressed this chi alpha. So basically, after some tons of algebra, you'll have a single expression like this. So basically, you're going to substitute all these things and translate everything back to the configuration space. Which is actually I have more details in these notes, but I feel I don't have time to cover all of them. But hopefully, you follow the logic and know that what we're doing here. Okay, cool. Then we have our equation, and we just summarize it as so C equals this. This is just the first line of this. Remember, this is like natural recycling. It's the first row of it, and we have the equations governing this. One thing I want to, the point here is that this epsilon alpha here is omega alpha plus these things. But if you actually care about this, B is just the omega spin cross product this. And Xi alpha and Xi alpha just normalize. So basically means that if your omega spin is much less than omega alpha, which is almost always the case, because many of these solutions depend on the traditional approximation, which basically this is one of their bases. And so your epsilon alpha is just almost omega alpha. So I'm using omega alpha here. Okay, and okay. So in principle, you can solve these equations, and then you are solving the tidal response. So one way of solving it is that we usually do in practice is by the adiabatic approximation. That is so if you look at this, so this is just decomposition. So if you really look at this equation, this basically, if you think about it, it actually means that if your tidal potential is doing your orbit at some frequency omega, then if you are making your adiabatic approximation, that means these coefficients they're also like doing it because they're the physical meaning of adiabatic approximation is that those phases just follows exactly as, or they're just changing quick enough that they can always follow the frequency of the outer potential. And if you do that, you will get a solution to, which I don't have time to cover, but we will have a solution that basically tells you the dynamical amplitude of this. Equivalent of solving this. So here, omega f is the external frequency of the tidal potential, the tidal forcing frequency, and then you still have this term. So remember that these Xi alphas, they are the free solutions, that is stellar oscillations without the tidal potential. So if you still remember that, so under the symmetry of the, so in the rotating frame, you can, these solutions are almost always proportional to a spherical harmonics, right? Because you are, because you actually do not do anything to the angular part of it. So as these solutions are to the, proportional to the spherical harmonics, so actually you can expand this tidal potential also in terms of spherical harmonics, so that only the tidal potential that is related to the specific spherical harmonic that can excite the oscillation that is with the same L and M.
Wait, so to be clear, you're saying zeta alpha is close to a spherical harmonic, right?
See, we're getting back to configuration
Like,
space, right? Yeah.
Right.
So
Like
does it-
even so in rotation, isn't it like a Hopf function, or is this?
Yeah, you are right. Technically speaking, that
So it's like close to one, probably.
right. So yeah, so the point I'm making here is that it's possible to decompose this. Of course, when the spin and orbits are aligned, it's possible to decompose this to spherical harmonics, and they're like closely to so basically across different L and M's is not many. There are not many contributions. So that gives you a way of calculating this thing, and as some final remarks, if we actually look at this, so remember that omega alpha is actually complex. So if we write it in terms of the oscillating frequency and the damping rate, so that gives you omega alpha minus omega force plus some damping rate, omega alpha, times a bunch of stuff. So now we're turning back to the physical meaning of it. So since we have the Hamiltonian, it's in principle possible to calculate the energy that is in each mode. And the energy is a way of understanding is the kinetic energy plus the potential energy plus the energy that is coupled with the tidal potential. So the energy that is coupled with tidal potential is actually never dissipates because they're just the gravitational energy that is when the fluid locates there. So so if we actually consider what can change in the mode energy, there is so we only have kinetic energy and the potential energy. The potential energy is basically the energy that's supported by the fluid, by gravity, buoyancy, pressure, these kind of things. So I have not yet rigorously shown that, but you can imagine that energy must be proportional to the amplitude square, because your displacement is here. So that means the energy in each mode is proportional to actually this. And if you look at this structure, this immediately gives you resonance structure. Actually, it's proportional. So another thing is that when you look at angular momentum, so the angular momentum is you can calculate it by something, with some derivative with this and the momentum, and this will give you. So this will give you, if we expand the mode in spherical harmonics, this will just give you an m, right? So it's proportional m times something that is proportional to the amplitude, and of course the momentum is also proportional to the amplitude. So that is basically proportional to this. So for the angular momentum of the mode, you'll notice that for m equals 0 mode, you don't have angular momentum, and for For all the modes, they have angular momentum. And physically, this is easy to understand because m equals 0 mode is basically just like the mode that is contributed by the sort of pushing and dragging force of the tidal potential, of the tidal force that does not have any angular momentum. Okay, so yeah, so I think I have enough mathematics today. So we can talk a few slides about the applications of this. So the first thing is that can you actually observe the tidally excited oscillations? The answer is you can. So for example, so this is a system. This is a light curve system called a Herbig star. And you notice that there's a huge sort of this. So this is in the time space. This is the Fourier space. So notice that there's a very large thing, and that is the equilibrium tide, as I already raised it. But you also notice all these high frequency things that appear here. And what is most remarkable is that if you put this in the Fourier space, you find that this frequency is exactly 26 times the orbital frequency. So that basically is a dynamical tide that is excited at the campaign. And all these things are just the equilibrium tide, they're just from sort of a continuum here. And this is from a Herbig star called KIC, this thing from paper by Jing.
So what is a Herbig star?
So the name is from this curve, right? So basically you see the luminosity doing things like this suddenly, right? Yeah. So if you want to draw the shape of it, it's actually a very distorted star, something like this. And there's a companion here, doing all this stuff. And of course, this is the equilibrium tide, so you see that long period but large luminosity perturbation. But you also have all these small oscillation modes that inside is providing the feature. Yeah. So first thing is that we can observe it. The second thing is that if you actually look at the expression for the energy and the angular momentum of the mode, so notice that for m equals 0 mode, it has no angular momentum, but it can dissipate energy. So how do you? So imagine you have a planet orbiting a star. So that means the planet is contributing energy, or is losing its orbital energy to the star, but it's not losing its angular momentum. So how is that possible? Well, if you feel like how is that impossible, that's correct, right? It is possible because the orbit of the planet can be eccentric. So if it's a circular orbit, you cannot lose energy without losing your angular momentum. But if it's eccentric, then basically you can't lose your energy without losing your momentum. And the fact is that you are circularizing the orbit without changing its angular momentum. And this is actually a very fascinating idea. It's a way of circularizing your orbit from the dynamical tides. Yeah. And another thing, actually,
this isn't a case where the n equals 0 mode is important, or?
Right. So actually, if you do this tidal expansion, you will find that actually the two most important modes are L equals m equals 2, or m equals minus 2, and L equals 2, m equals 0. So these two modes, so if you really expand these two modes are the most important. Their expansion coefficient is the largest. Yeah. So for this mode, they are dissipating energy and angular momentum, so you can have orbital decay. For this mode, you are only dissipating energy, but no angular momentum. So if it is circular, then it's not dissipating energy as well. But so basically, the point I make here is that this process can happen, and I think it's very fascinating. Yeah. So I actually intend to talk about resonance locking. I think I still have time for it. Another process that might be I find very interesting is called resonance locking. So the idea is here. You have, so imagine you have a star, and you solve for all the oscillations at different stellar age. And you will find that even for the same mode, their oscillation frequency is changing because during the stellar evolution, the internal structure is changing. So you will find you end up with like these curves. So each line represents a mode. And so each line represents an omega alpha. And the reason it's increasing is due to, I don't want to review stellar evolution, but you just believe me there. Yeah. Okay. So now you imagine that you have an orbit with an orbital forcing frequency, let's say initially here. Okay. So say that at first it is not close to any of this omega alpha. So you look at this, you find that this tidal energy and the energy dissipation is the largest when it is near one of the omega alpha. So at first you are not near it. So of course you're still dissipating energy, so you change, but not on a very excessive rate. But when you are getting close to one of those omega alphas, then basically you are dissipating a lot of energy, and that will cause your orbit to decay faster, and that changes your orbital, the tidal forcing frequency. So it will like win up, right? Because slope is basically the rate of omega alpha is changing. So there could be a possibility that these things are exactly parallel to each other. So notice that this is actually a stable equilibrium, because if you are getting closer, then you are changing your. If you are getting closer, then you are dissipating more energy. You are losing more orbital energy. So you must go to that direction, which is faster change of omega f. If you are getting farther, then you are getting less energy dissipation, so you must be back. So the mere result of it is that then you end up that your forcing frequency follows the evolution of one of these modes. And that is called resonance locking. And that gives you an estimate of the orbital decay timescale. Since they are always changing with one of the modes. So the orbital decay timescale must be like the mode variation timescale, which is in most cases just like the lifetime of the star. Okay. So this not only can happen in stars, but it can also happen in planets. So we talk about stars all the time, but this oscillation also exists in planets. So one thing that from Jing's paper is that so most people calculate the tidal migration of the moons of Jupiter, and if they are using the equilibrium tide theory, that would predict a constant tidal quality factor, which we talked about at the start of the lecture. That is the phase lag, because it's physically interpreted as a phase lag between the bulge and the orbit, so it must be the same. The actual measurements show that for all these moons, the tidal quality factor is much different. It's actually very different. But if you translate all these Q quantities to the tidal migration timescale, you find that they are remarkably similar, and they are almost exactly at the timescale of 10亿用英语怎么说？
什么
？10亿是多少？是
I don't know what that means.
Anyway, like the age of the solar system, trying to think about the numbers. Sorry, it's hard to think about numbers in English. So that is evidence that actually these moons can migrate. So their tidal migration is actually the process of resonance locking that provides a constant tidal migration timescale instead of a constant Q. Yeah. So this is measurements from Linhao 2019. Yeah. Okay, so I think that's all. That's not all I want to talk about today, but that's all I can talk about today. Yeah. So if you want to follow like more details in this mathematics, I think you can look at the notes. And yeah, thank you. Sorry for not getting the time well, but yeah.
No worries. Anybody have any questions?
Yeah, can I ask, can you go back to that slide with the heartbeat stars?
Yes.
Why again was the frequency 26 times the orbital frequency at any test?
So if you expand this potential, you generally have a series of a sum of a series of the
YLMs?
YLMs. And in the YLMs, the M dependence is e to the I omega phi, right?
Sure, yeah.
And phi is the one way to think about it, phi is basically just omega t. If you are orbiting with omega, so that means a tidal force is actually providing. That means a companion is actually providing tidal force at a very different frequency that is proportional to that they are all there. So the tidal force in frequency in a circular case is m times omega orbit minus omega spin. The m comes from the spherical harmonic expansion. So for some reason that I cannot tell you why this is 26 but not 25, but for some reason this some of the high order oscillations are exciting this system.
Okay.
So we say So yeah, I only tell you that why this is an integer, but not why it is 26. That's specific to this system. Yeah.
Gotcha.
Is that power spectrum on the bottom? Is that data or is that simulation? Or like
it's data.
calculation?
It's data. Yeah. It's
data.
measured, yeah. So it's exactly 26. Here. So that is pretty amazing. So this paper is very technical to read. I don't think Jim even remembers anything he ever wrote down. Everything, not anything. He remembers something.
Any other questions? All right, let's thank Linhao again. Next time is Keith.
Keith?